we were talking about sort of reviewing the POGL activity that you did to learn about VSEPR shapes, or molecular shapes. Sometimes we call them VSEPR shapes, but molecular shapes. This concept that molecules are not just letters on a two-dimensional piece of paper, but that molecules themselves have three-dimensional shape. And since we live in a three-dimensional world, you know, it's pretty clear that the stuff that makes us up, the molecules, must themselves have some three-dimensional shape. Okay, so I wanted to tell you that you really need to practice working out molecular shapes. Just like the Lewis structures, you don't want to try to memorize all of them. It's a puzzle. You want to have the skills and be familiar with the rules so that you can work out Lewis structures. Same thing is true with the VSEPR shapes, the molecular shapes. Once you have the basic concept and you remember the names of the geometries, you can predict based on a chemical formula what the shape of that molecule is going to be. So here's one, beryllium dichloride, this one right here. Now this particular element, beryllium, I don't know if you remember or not, but it breaks the octet rule. It only needs 4 valence electrons to satisfy its octet. Okay, it only needs 4 valence electrons. All right, so that's something a little bit special about beryllium. Given that information and knowing that it itself has 2 valence electrons based on its position on the periodic table, and chlorine each has 7 valence electrons, that tells me that in this particular molecule we have 7 plus 7 is 14 plus 2, 16 electrons to work with to work out the Lewis symbol. And also, if you go through the S equals N minus A rule, you'll find that there's only 2 bonds in this molecule, and all the electrons can be placed like that. That's the Lewis structure. And so from the Lewis structure, I can see there's only 2 regions or 2 domains where there's electrons. There's electrons right here. Remember, a dash is a pair of electrons, and there's electrons right here. That's it on the central atom, which is beryllium. And so since there's only 2 regions of high electron density, or 2 electron domains, that tells me that the geometry, the electronic geometry of this molecule must be linear. And since there's 0 non-bonding pairs of electrons on the central atom, that tells me that the molecular geometry is linear as well. So when we're looking at the molecular geometry, we oftentimes don't include all those non-bonding pairs of electrons. We just draw the elements that have atoms in the structure. And so this would be linear molecular and linear electronic geometry with a bond angle of 180 degrees. All right, you should know how to do that from working out the POGL. And then ammonia, of course, we've seen this a gazillion times. You have the Lewis structure that looks like this. You have a total of 1, 2, 3, 4 regions of high electron density, or electron domains. That tells me that the electronic structure, or the electronic geometry, is tetrahedral. But since one pair of electrons is a non-bonding pairs, the molecular geometry is going to be trigonal, pyramidal. Okay, and when we draw this, there's a certain way we want to indicate the three-dimensional shape. When you draw the Lewis structure, it just looks like everything is in the plane of the paper. But when you're drawing the shape of something that is not planar, we use this symbol of a wedge and a dash. And a wedge means that the bond is coming out of the plane of the paper, and the dash means that the bond's going behind the plane of the paper to try to indicate some three-dimensional nature. So this is the standard way that people indicate three-dimensional nature, is with a wedge and a dash. Okay, so those are just a couple of examples, but you should have worked plenty in the POGL activity, and there's plenty in the homework, and so you want to be able to do that with ease and remember all the names.